Yes, so welcome everyone to CFPU seminar. We're very happy to have, particularly happy to have as well, Yiming Zhong. He did his undergrad at Nankai and his master's at Perimeter. Studied his PhD under Ruben Essig at Stony Brook and is now in his second postdoc. His first postdoc was at BU and we overlapped there when I was a grad student. So I know him, I like him a lot. And he's now a postdoc at the KICP at Chicago and we're very happy to have him tell us about using self-interacting dark matter to seed supermassive black holes. So take it away, Yiming.
Okay, thank you very much for your nice introduction, Manuel. And thanks for everyone for coming. Happy St. Patrick's Day. So my name is Yiming Zhong. I will talk about seeding supermassive black holes with self-interacting dark matter halos. And this is a work in collaboration with Wei Xiangfeng and Haibo Yu at UC Riverside. So we already posted a paper last year, and we will post a companion paper very soon, like this month. Oops. Okay, so here is my outline. First, I will introduce you to the growth puzzle of the high redshift supermassive black holes, SMBHs. And then I will turn into another topic, self-interacting dark matter halos and the gravothermal collapse of the SIDM halo. And then I will try to build a link between the two and to see if there's a pathway to seed the high redshift supermassive black hole from the SIDM halos. And then I will also talk about two obstacles along on the pathway. And finally, it's my summary. All right, so like every cosmology talk, I will start from this diagram of the cosmic history. And we know our universe is 14 billion years old. And we have passed several different phases during the evolution of the universe, starting with the Big Bang, and there may be inflation, and then there's recombination, dark age, reionization, then dark energy dominates, and finally we arrive today. So one interesting thing people observed during past decades is that there's a population of supermassive black holes in the reionization age. And so that is observation by several different telescopes, by analyzing data from several different telescopes, like Subaru, DS, Pan-STARRS, and SDSS. So here is kind of a summary plot. So on the vertical axis is age of the universe, and on the horizontal axis is the black hole mass. On the upper panel, it's the redshift. We all know that for star formation, it's around z equal to 30, and but for the for the black hole observation, we found it's can be as high as z between z equals 7 to 8. So to put it more quantitatively, we found 7 black holes with mass greater than 10 to 8 solar mass at a redshift greater than 7, and we found 200 black holes with mass greater than 10 to 6 solar mass at a redshift greater than 6. And when we see something like so ancient and so giant, like very naturally, we will ask the question, how do they form? So there's a standard story is that they form by some seed black holes from the collapse of very ancient stars. Those stars are called POP3 stars, most made by heliums and hydrogen. And after the seed black hole forms, they began to accreting baryons on top of that. So their standard story is so-called Eddington accretion. The basic idea is that for the baryons attracted to the black hole, given the gravity, but at the same time, black hole kind of push the baryons away due to radiation pressure. So there's a balance between radiation pressure and the gravity, and this is so-called Eddington accretion limit. So on the Eddington accretion limit, your black hole mass grows from seed black hole mass according to some expansion law. And it's controlled by a factor of the elapsed time of the accretion process over the E-folding time. And for the E-folding time, it's like 450 milliyears times some accretion coefficient epsilon, which depends on how do you do the accretion, and divided by the so-called Eddington coefficients ratio, which is defined by the bolometric luminosity over the Eddington luminosity. So that is just a coefficient, tells you if you saturate the Eddington accretion limit or if you are not saturate the Eddington accretion limit. So again, looking back the pop 3 stars, if you have a pop 3 stars, you see the black hole is very likely have a mass between 100 to 1,000 solar mass. And then you do Eddington accretion, you always saturate the Eddington accretion limit. So in the end, you can get this supermassive black holes between redshift 6 to 7 with mass like 10 to 8 to 10 to 9, pretty standard story. Of course, we also observed the Z = 7 supermassive black holes. And if we put back the story of Eddington accretion there, there's something become like more challenging. So if we think about the J0313 1806, this is the most high redshift supermassive black hole we observed, and take its mass and take its redshift and run back story of Eddington accretion. We found that we need something as massive as 10 to the 4 solar mass, some black hole as massive as 10 to the 4 solar mass at Z = 30, which this is far greater than the mass of pop 3 stars. So we need something else to solve that. Of course, astrophysicists have long working on that, and there are several different ideas. So one idea is from the direct collapse of the pristine gas, which is pioneered by Amuka and Loeb and Brown like 20 years ago. So from the direct collapse of a pristine gas, you can have a seed black hole of a mass like 10 to the 4 to 10 to the 6. Then you again assume the accretion is saturated to the Eddington limit. Then you kind of naturally can explain the J0313 1806. But the growth puzzle of the high redshift massive black holes are not stopped there. So the problem is that we not only observe the black hole mass redshift, we also observe the black hole luminosity. So among the high redshift,
Yiming, sorry, can I ask a quick question?
Yes.
For a non-expert, what is a pristine gas? What does that mean?
Oh yeah, sorry. So for pristine gas, it just means after the gas falling into the halo, it does not form structure like stars. It's directly collapse towards the center and form black hole.
Oh, so it hasn't formed structure, you're saying?
Yeah.
Okay.
Can I just make a comment here?
Yes, please.
So pristine gas, it's not necessarily just structure. It means primordial gas in the sense that it has not been enriched with metals. That's
okay. Yeah, that's right. That's right. Yeah. Yes.
Gas, right? So it hasn't been enriched with metals, and therefore it is the primordial abundance. Basically one every 16 atoms will be helium, and that's about it.
I see.
Okay, thank you.
So there's no leftovers from star graveyards and.
Yes, and this is critical because if there were metals, then that changes the the cooling mechanisms for which you can form the first stars, population 3 stars. So you need to have absence of metals in order to form these very massive objects. And I think that's what Yiming is talking about, right?
Okay.
Yeah, thank you very much. Yes.
And sorry, piggybacking on this and taking advantage. There's a bunch of black holes here. Those are low redshift. What's the standard story? I mean, I'm no astro, so what's the standard story for the formation of these supermassive black holes?
I think the standard story is just a stellar collapse, stellar black holes, and then maybe you have a merger, you have an accretion, and then you can reach
these high masses, and you just have enough time to do this. All right, thank you.
Yeah, sorry, it's on the log scale, so it's
yeah, of course, yeah. Good, thanks.
It is still an unanswered question, though. The suspicion is that mergers can give rise to that because there's much more time, so you can assume that there's enough time for mergers to really give rise to these massive ones. But the interesting question is what Yiming is talking about: these, high redshift black holes, how did they get to be so big? So yeah.
Right. Okay. Thank you. Thank you.
Yeah. Thanks very much, Travis. So let me keep talking about the growth puzzle. And there's something I will call like even more challenging than what you see before. I will call it a growth puzzle 2.0. Now, one challenging thing is we observe there's a population of low luminosity supermassive black holes. And so their Eddington accretion coefficient is actually pretty low, like much smaller than 1, which means their accretion process is kind of very slow, very inefficient. And if we assume that Eddington accretion rate is all the way starting from its formation, that we need something supermassive, like 10 to 8 or even bigger solar mass object, like seed black holes at z equals 30 and to starting with. And so that is far above the mass, like usual people think about what the direct collapse of a pristine gas can offer you. So this is more challenging.
But Yiming, we measured the luminosity presumably today, which is at lower redshifts, or do we actually measure these things at high redshifts? Are these measured supermassive black holes actually measured at those redshifts?
So those are measured at a low redshift, yes. And yeah, maybe you mean there can be some sudden change of the
exactly. Like perhaps the system changes over the evolution of the supermassive black hole.
Well, how can you make a supermassive black hole smaller? I don't know of anything that can do that, right?
Well, I guess I don't really know the measurement of this luminosity that's being measured. I guess I don't really know whether that's necessarily fixed as a function of time, or this luminosity.
I think what it may point to is perhaps a systematic where we assign larger black hole masses to observations at high redshift. Perhaps.
So let's just make sure if there's if you're talking about like those black holes are unlikely due to the low accretion rate, low luminosity, and I think Jeff is asking if if at a very high redshift you can have a very high Eddington accretion rate. And just maybe at a low redshift, you just suddenly change it to the low Eddington accretion rate.
But yeah, Eddington says
I'm not sure what mechanism would cause that, but yeah.
Yeah, I don't know. I have no idea.
Yeah, I think it's that's a very good point, Jeff. I will refer you to look at this paper on in 2019, and this is the observation paper. Like from Subaru telescope, and I think they have some arguments, like they assume maybe it can last longer than just around z equals 7. But I think I think you are right. There's certain possibility that it's first do very fast Eddington accretion, then then become like flatter in the end.
Yeah, I mean, one example would be maybe some merger that took place that might have changed the evolution of the supermassive black hole from high redshift until today, or until redshift 6. I'm not sure if that's sufficient to do this, but maybe that'd be one option.
Yeah, that's okay. Yeah, that's maybe a possibility. Okay, but here we just pick up like one simplest scenario, like if you just assume a simple identity accretion of all ways through the history, it seems cannot explain those growth puzzle for those low luminosity supermassive black holes. Just that. And there's another puzzle. There's a population of so-called young supermassive black holes. And so people have a proposed idea to measure the accretion history of the supermassive black holes using the proximity zone method. So basically the idea is that supermassive black holes are shiny, so they have a UV light, and this can reionize the neutral hydrogen surrounding it. So by measuring the size of this reionization zone, you can kind of infer how long its accretion history is. So basically, people found there's maybe like some supermassive black holes with super tiny accretion passing time, like smaller than 0.1 milliyear, which I cannot even show on this plot. For such a short period of accretion time, seems no way that identity accretion story can work. All right, so this is a challenge from this high redshift supermassive black holes. As people expected, maybe we can see more low luminosity supermassive black holes. Maybe we can see more young supermassive black holes in the near future. And the question is, of course, like how to form the supermassive black holes. And our idea is that maybe they can form from the most massive object in the universe at that time. It's from the dark matter halos. But maybe we should first answer the question: why does dark matter halo collapse? Okay, so that's my first part of my talk, and then I will go to the SIDM part. Is there some other questions? Okay. So I would argue that collapse will happen for self-interacting dark matters. And as we all know, the self-interactions are very common phenomena among normal matters. You can have self-interaction between photons, like nucleons. And that's the same thing also may be true for dark matter, especially you think about the dark sectors. And actually people work out all different self-interactions, like simple contact interaction, or some long-range Yukawa interaction, or some number-changing interactions have been all proposed. And when people talk about self-interactions, usually there's two axes in the parameter space. So one axis is self-interaction strength. It's measured by center square per gram, which is roughly 2 bar per GeV. Another axis is the relative velocity of self-interaction. So what this axis really tells you is what scale of the astral system you are considered. So we know that from small to larger, there's several different self-gravitating astrophysical systems. There's dwarf galaxy with mass 10 to 8 to 10 to 11 solar mass. There are Milky Way galaxy with mass 10 to 11 to 10 to 14 solar mass, and there are galaxy clusters with even larger mass. And at different, all those different galaxies can be characterized by different variable velocity. So here is a plot of some like current constraints on the self-interaction. all the arrows just show you the allowed values. At a galaxy cluster scale, we have the Boolean cluster constraints. When the two Boolean cluster crossing each other, if the self-interaction is too strong, the dark matter would be like a gas sticking into the center, and which contradict from the observation. And the Milky Way scale, we have the galaxy morphism constraints, because the self-interaction are more likely to randomize the velocity distribution of your dark matter particle. So if the core of your galaxy are more likely to be spherical rather than triaxial. So if you observe something triaxial, you can place some constraints on that. And on the smaller scale, on the dwarf scale, we have a gravothermal collapse, which I will talk more very soon. And let's don't forget that self-interactions are proposed to solve some small scale problems. So here is a list of favorite values that can solve some small scale problems, which I will not talk too much about. So how the self-interactions works, like how it actually solve those problems. The idea is actually pretty simple. Once you turn on the self-interaction, then your hot particle, when meet with a cold particle, it can transmit some kinetic energy to the cold one. So microscopically, you will see the halo become thermalized. So here is just a case. We run the on-board simulation for Milky Way sized halo for 10 years. I believe, assuming the self-interaction strength like around 2 centimeters square per gram. And initially, our halo we assume the halo to have an NFW profile, like this black line. So after 10 billion years, what we observe is this blue line, which you can see the inner cusp profile disappears. You have a very flat, large core. And when you look at the 3D velocity distribution profile, what you see is that the colder part of the inner halo become also like thermalized with the hotter out part. And that's the reason behind which driving the cusp profile into this core-like profile. And so that's the way it solves the cusp with core problem. And but the story is not stopped there. So as a self-gravitating, finite size self-gravitating system, the SIDM halo has something weird. So we know that for such a system, it follows the Barrow theorem, 2 times kinetic energy plus potential energy equals 0, which means its total energy actually is negative. And if we assume equipartition theorem, the kinetic energy is proportional to temperature. What we found is the total energy divided by the temperature is negative, which means the system seems to have a negative heat capacity, and that's what leads to gravothermal collapse. So here just a more cartoonish picture of the gravothermal collapse, like what's happening. So let's take the core region of a halo, what we saw before. It's follow some isothermal profile, which means all the particles follow some velocity distribution, say Maxwell, Boltzmann-like. And there is always some particles that kind of live in the tail of that velocity distribution. And they are likely to be evaporated from the halo. So after evaporation, you can re-evaluate what's the total kinetic energy of the halo. It goes down. With total potential energy, it goes up. But overall, you will find when you add them up, twice of kinetic energy plus potential energy, now it's smaller than 0, because what you room out is the most energetic one. When the system out of Barrow, it means gravity is no longer supported by the random motion. So the halo collapse a little bit. So in order to back to the Barrow, after the collapse, the halo also need to increase the temperature a little bit, such that the kinetic energy plus potential energy back to 0. However, when you increase temperature, your velocity distribution becomes faster, which means there may be more particles now living in the tail are likely to evaporate. So in the end, you get a loop. When your halo collapses, your halo becomes hotter, and you evaporate more particle, and then your halo collapses more. So there's so-called runaway collapse process, also called the self-similar collapse process. So here's just a movie I made. So the horizontal axis is the radius, vertical axis is the density. So here is just show you like a density profile. On top, I show what's the time it takes to make this snapshot. So now I run the movie. As you see, very quickly, the Kavli profile develops to be core-like profile. But then it seems to stay there. But as time gradually goes on, you can see the core-like profile began to collapse inward. And in the end, it will stay at some end states like that. But like what happens at the end stage of the gravothermal collapse, what we see is that halo fragments into two parts. So there is a ultra high central region, a ultra high density central region with a mass likely to like 10 to minus 3 to 10 to minus 2 of the total halo mass. And there's a very Kavli dark matter envelope surrounding the central region. We see from this picture the dark matter fragment in this two part. So there's many people think that that's very high density central region will collapse into a massive into a black hole, and because it's like a 10 to minus 2 of total halo mass, that will be massive enough to see that there's supermassive black holes we observe at early redshift, high redshift. But there's a problem. The problem is that when we think about a cross section sigma over m, you have 1 centimeter square. It takes the order of 100 years to reach that end state. In other words, the collapse will happen, but that's in the far future, and not in like within 700 or 800 million years of universe time. So that's make us to think if we can do something extra to save this very nice collapsed SIDM story. So and now I will take the pathway we take. We need something called baryons. So probably as we all know that dark matter halos attract baryons. And when the baryons are compacted at the halo center, it can actually deepen the gravitational potential there. And now when your dark matter inflow, it will become even hotter after relaxation because your gravitational potential got deepened. And that will feed into the runaway loop and accelerate the gravothermal collapse. So that's our basic idea. And to put it more quantitative, we need to run simulation. What we do again, like our previous paper on the Dissipate SIDM, we run a 1D semi-analytical fluid simulation. So in this new simulation, we treat the SIDM to be dynamic. So we trace all the properties of SIDM, and we treat the baryons to be static. So it's just to always give it a static gravitational potential for the baryons, for the SIDM. For the SIDM, we separated the halo, SIDM halo, into many shells, and we assume each shells in its own like local thermal equilibrium, and all the SIDM are in some kind of hydrostatic equilibrium. And for the baryons, we just simply assume it dominates gravitational potential in the halo center and insert gravitational interaction like efforts to the SIDM through the hydrostatic relation. we do not consider the back reaction of SIDM onto the baryons distribution. So this is our setup. And then we run our semi-analytical fluid code. There is a heat conduction step. After heat conduction step, the halo may be out of barrel, and we do the hydrostatic relaxation to bring the halo back to the barrel. And then we keep doing that. And so here's more details about setup. I will skip them. If you have more questions, we can come back. Here's a list of transportation equation, Euler equation, first law of thermodynamics, and the closure condition, the conductivity equations. And here's our boundary condition. Yeah, in particular, I should say what our initial conditions are. We don't observe that good, for the high redshift halos. So for that, we rely on the simulation. So we take a cosmological hydrodynamic simulation of Weiss et al. 2008. So they simulated some protogalaxy at the around 17, and they found basically dark matter follow some NFW profile, and baryons follow some single power law profile. So that's the data we take, and then we fit it with this two hypotheses. And as you can see, the baryons dominate the central region. So here's our results from the simulation. Yeah, I should apologize a little bit since all our simulation are done in the dimensionless manner. So there's always some fiducial quantities we model out. So in this plot, the horizontal axis is dark matter enclosed mass, and vertical axis is the dark matter density. And for each line is a snapshot at a different time. And we found that the dark matter enters deepen into the end state around t equal to 8.41 T0. So compare to the pure SIDM case, we found several features. One is there's no cold expansion phase. The halo starts to collapse onset when the simulation begins. And also we found that the collapse time is shortened by a factor of 100 compared to pure SIDM case. So this is more obvious when you look at this insert plot, where the horizontal axis is evolution time, and the vertical axis is the average density for the inner part. You can see that the collapse is shortened by a factor from 10 to the 3, from 1000 T0 to 10 T0 when you add the baryons. And also we found the enclosed mass for the central region. This time it's actually smaller. It's 10 to the minus 3 of M0 compared to the pure elastic case, which is 10 to the minus 2. And we verified this result using a different baryon assumption. Previously with a single power law, we also tested for the Hörnquist profile, and we found a similar acceleration process. Also, I should point out, so there's some unbodied simulation paper, one is by Yang and Yu, one is by Samini, published this year, where they also observe accelerated halo collapse process when including baryons into the SIDM halo.
Do these embodied simulations include feedback from SIDM to baryons, or still assume just some static baryons?
Yes, so for the Yang and Yu, they do not, but for Samini, so they include the feedback of baryons, and they found the feedback does not change the story.
Okay.
Yiming, I have two questions.
Yes.
The first one, a little bit about gravothermal collapse. Does that happen for halos of all sizes, or is it just? I mean, I'm thinking, why would would that be still happening to our halo in our Milky Way, for example, or any of this? Like, and why aren't we seeing this collapse?
Yeah, I think for Milky Way, I'm not sure. I'm not sure if the collapse actually happened or not happened, because for Milky Way, it's a pretty a deepened potential. For our simulation, we do a dimensionless simulation, which means our simulation result in principle apply to all the systems.
Right.
But there's several constraints, several assumptions in our simulation. One most important assumption is we assume it's a fixed baryonic background, right? Which is true when your baryons are very compact at the center. In other words, if your baryons are very dilute, then this will not happen, because there your SIDM can actually push away all the baryons do the usual expansion, and there would be no feedback loops.
I see. Okay, so this is gonna be just for a certain class and of systems that presumably exist at this earlier redshift, so that you can have this behavior.
Yeah,
right?
I will agree with that. So just maybe by chance you have some system with very compact baryons in the center, then you will observe this kind of collapse. Yeah, but of course the question is, where's the boundary line? Like, how do you define what's the very compact baryon distribution, right, or very diluted baryon distribution? And so for that part, we haven't we don't have an answer, and that requires more simulation. Yeah.
And question, thank you. And question number 2 is I guess that's what you were gonna answer in a little bit, right? You need to, at the end of this collapse, it needs to give you a black hole, right? So what are the conditions on the enclosed mass or rho chi, right? Is this 10 to the 12 that I'm seeing here, right? And enough? Is that enough density to produce the black holes, right? Which is the end result that you want?
Yeah. So I will answer that question in my later slide.
Okay.
But for now, let's just assume the entire central region, as you see, the central region collapsed to the black hole for a while to see if there's a pathway there. But then I will come back to is that okay?
All right. Thank you.
No problem. Is there more questions?
Yiming, I have a question that's less directly related to the picture you're talking about. So I just wonder, in general, for the gravithermal collapse, you assume the elastic scattering in this picture, right? So I just wonder, in general, how does for example, a dissipative sector would affect the gravithermal collapsing scale?
Yeah, that's a very good question. So in our other paper, I had with Ruben and Sam and Haibo, and we try to think about a kind of simple dissipative model. And there we also found that the collapse can be accelerated. But if you try to use the dissipative model to form supermassive black hole, there will be some problem. The problem is that, so in the end state, your dissipation at the central region can be very large, which means your center part may be big, and some so-called fragmentation may happen because there's a strong cooling effect. Because in the end, your central region will be a very high density, and you can calculate what's the cooling time will have. If the cooling time is smaller than dynamic time, means maybe a central region were fragmented to a bunch of dark clumps rather than all collapse into a single black hole. So that's something we try to avoid in this paper.
I see. Thank you.
Yiming, I have a question as well. So if this happens early enough, would you inject enough energy to have an imprint on reionization?
What's reionization? Neutrino. Sorry.
No. Reionization is the time when the universe went from being neutral into being ionized.
Mm-hmm.
And so my question is there enough energy ejection that can have an imprint on when that process takes place, and whether that can affect, for example, the power spectrum of the 21 centimeter line, or any other cosmological large-scale effects aside from just individual halo predictions?
Okay. So what do you mean by injection? I assume you're most talking about the dissipative dark matter. Oh, like you just talk about this just a normal SIDM halo. Just make sure. If it's a dissipative dark matter, I assume you can inject some dark photons into the surrounding medium. And yeah, that depends on how large your dark photon like couplings to the normal hydrogen. And it may have some effects, or you can place some constraints.
Okay.
Yeah.
Okay, I'll put some more thought into it. Thank you.
Okay.
Thank you.
Yeah, I think there's some atomic dark matter study like on top of this. Like people try to place some bonds there. Okay, let's just continue my story. I think I don't have too much time. So we can put our simulation result back to the cosmic background. Let's look at some like low luminosity supermassive black holes. One example is what I showed before. It's this J20050000, which have identity accretion like around 0.1. So in our SIDM story, the pathway is that you have a galaxy with mass like 10 to 11 solar mass, between 10 to 11 solar mass to 10 to 12 solar mass, and then you have a self-interacting cross section like around 1 centimeter square per gram. Then your halo can collapse into the seed black hole within like a few hundred million years. And then you don't need to do much accretion because your mass is already very close to the observed supermassive black hole mass. So the story is solved. So in general, we found that this kind of cross section and this kind of halo mass can explain all the low identity accretion rate supermassive black holes on this plot. And all you need is some dark matter halo with the size of galactic size. All these halos need to have very compact baryons. And your cross-section strength requirement is not so strong. It's just 1 centimeter square per gram, like very normal for the low redshift. And also, maybe also very important is that your halo concentration, you don't need to be so large. Like you only need to C equals 3 rather than some large concentration scenario people have assumed. And also same thing will happen for the other like dark supermassive black holes with a much higher identity accretion rate. All right, so finally, allow me to spend a few minutes to talk about a few like obstacles in this story. So far, our story is that you have a Milky Way size halo with a compact central baryonic component, and it could give you 10 to 7 to 10 to 9 solar mass high density central region. And that central region will collapse into seed black hole, and they will then give you the low luminosity, high redshift supermassive black holes. And there's a missing link is that if the, as Manuel asked, if the central high density central region will really give you the seed black hole, many researchers just assume that will happen, but we need a more like a quantitative answer. So there's two questions, two obstacles on this pathway. One is there's constraints on the angular momentum of the black hole, and you need to satisfy that. Another one is that we need to examine if the ultra high density central region really triggers the gravitational instability and make that part collapse into a black hole. So for the first question, it's actually we try to answer in our paper. So as you all know, like halos naturally have some angular momentum, either from tidal torques, from primordial field, or from asymmetrical collapse process, or from major merger. This can all bring the halo with some angular momentum. And for the black hole, it's have a maximum value for the specific angular momentum. It's roughly like G over C times black hole mass. So we found that for a typical halo, we considered the specific angular momentum is around 10 to the kpc times kilometer per second. But for the seed black hole, we need to consider its specific angular momentum. It's like 10 to minus 2 kpc kilometer per second. So it can be a factor of 10 to 2 to 10 to 5 times larger than the maximum value allowed for seed black hole. So that means we need some mechanism to dissipate the angular momentum. Fortunately, we found that self-interaction itself may be the answer. We know that the self-interaction introduced some conductivity between different shells. We think that it also introduced some kind of viscosity between the different halo shells. And because of the viscosity, there's some shell pressure between different shells, and that shell pressure can transport the angular momentum from inner region out to the outer region. And by some analytical modeling, we found that the angular momentum change rate for the inner region is actually proportional to the angular momentum itself, which means now you have some exponential law, and that will be a very efficient way to dissipate the angular momentum. And by some estimation, we found the central region that will collapse into black hole will become effectively non-rotational soon after the gravothermal evolution starts. And that dissipation timescale, it's only like order 1% of the total collapse time. And for the second question, we wonder when the central region becomes actually unstable. And to answer that part, maybe we can first take a look back at the Newtonian limit of a star. And yeah, most natural thing we do is we open the MTW and look at what's the answer. So it tells you that when the adiabatic index of the system, the gamma, reaches 4/3, then the system becomes unstable. And to see that, you can from a simple ad hoc argument here, like you assume that your system have a balance between the gravitational force and the pressure, and in this way, and then you perturb that boundary of your star a little bit, and then you look at what's the response, and you find that the delta R follow this simple harmonic forms of equation, which is kind of crucially dependent on what's the sign of gamma minus 4/3. When the gamma is greater than 4/3, the system is stable. When equal to 4/3, the system is marginally stable. When gamma smaller than 4/3, your system is unstable and develops some tachyonic mode, and the system just collapses. Okay, so that is for non-Newtonian limit. So in our paper, we do something better. We consider the general relativistic instability condition, and we assume the SIDM follows some truncated Maxwell-Boltzmann distribution, and then we solve the Tolman-Oppenheimer-Volkoff equations and impose the Chandrasekhar criteria for the position equation. What we found is that the system gradually involved from the stable state. So again, this gamma this red line you can view as gamma in the previous page, and this a black line you can view as updated instability criteria. It's no longer a constant for 3, but actually have some dependence on the states. And we found that the instability can be triggered when the velocity dispersion at the halo center reaches 0.57 of the speed of light. All right, so this is just one criteria based on the adiabatic index. We also test looking at some other criteria like people used in the literature, the total energy criteria, the bending energy criteria, the fractional bending energy criteria. And we can organize all the different criteria for the evolution of this central region of the SIDM. And this we summarize in the paper will appear soon. All right, so finally here is my summary. I hope I convinced you the high redshift supermassive black holes really bring some challenges to astrophysics and require some new thinking. And we think that the SIDM plus baryons provides a possible pathway to form this high redshift supermassive black holes. Of course, we need more simulation and more data to verify that. And in the near future, maybe not so far near future, James Webb Space Telescope and the Vera Rubin Observatory will bring us more data or more observation, which we can deep over understanding of those creatures. Thank you very much.
Thank you, Yiming. It's very interesting. Are there any more questions?
Yeah, actually, I have 2 questions, if you don't mind. So I'm still, I mean, very, very nice talk, very interesting. But this reminds me of a recent paper by, I'm sure that you know, by Fire, where they had a slightly different model. I mean, they have this dissipative interaction sector, and also they have the elastic scattering. I think, if I remember correctly, they fixed the ratio between these 2 cross sections. And I remember their message was like the timescale for gravithermal collapse was slightly different from what you show, and also for the dissipation of the angular momentum, there was also a little bit different because they were seeing some moderate flattening at the small radii. I mean, could you comment on that?
Yeah, so I haven't checked the Fire. Yeah, I saw the Fire paper, but I haven't checked all the details like very carefully. But yeah, the big difference is that, of course, they do a more relativistic setup. They have a baryons, they have a feedback, like everything. Okay. And our study are mostly like a fluid model, dark matter only. And we expect there will be some difference, but I think the quantitative trend will be kind of similar. Like for the dissipative dark matter case, you can check our paper with Huoran and Haibo Yu. In that paper, we just compare the unbodied simulation with the fluid model, and just from that unbodied simulation, which is dark matter only unbodied simulation, we saw that dissipative effects, which means the halo collapse get accelerated, but the amount of acceleration is not as big as the fluid model considered. So there are already some discrepancies. But of course, a more relativistic setup, I expect you can see maybe the discrepancy is bigger, but I expect the quantitative trend will be the same.
Right, right. I mean, I remember one argument was that they were saying in the paper by you and Reuven, you assume the equilibrium to be maintained like all the time, right? And I think they were arguing that if the dissipative, although I don't really understand this statement, if the dissipative cross-section is large enough, the distribution of the velocity could deviate fairly largely from the Boltzmann distribution. and they were attributing the difference from to some of the difference to this deviation from the equilibrium. So I don't know if you
yeah, so that's a good argument. So in the fluid simulation, we always assume the halo in some quasi hydrostatic states, which means the gravitational potential is always balanced by the gradient of the pressure. That's may not true. That's may not. I mean, that's certainly not true for the cold dark matter case. For the SIDM, because it's have more frequent interactions, so I would expect that will actually bring the system more to the hydrostatic states. So I'm not sure if that's really the reason behind that. But I will take a second look.
I see. Thanks a lot.
Yeah, no problem.
Any more questions?
I guess I have a related question. So in your study, you assume a static baryon, like a central region, but if you have and even even if ignoring the feedback from SIDM to the baryons, the baryon itself could be have some dynamics, you could have formation of just due to baryons, like this supernova, AGN stuff, all these things, right? So
yeah.
So yeah, the reason I'm asking is that, of course, I know it's difficult just to treat them like in your case. I don't know whether there's any planning for any simulations to do that, and also we know that even before there's people talk about just using the baryonic activities to explain the cusp core, right? Just to explain dark matter core. So
that's right. Yeah. Yeah. I think I will refer to this paper somewhere at all, which add the baryonic effect and look at what will happen. And I think it's still what they show that the most important factor is there's the baryons deepen the central potential and your collapse accelerates. And secondary effect is there's a feedback process, which kind of will slow down your collapse. So that is secondary compared to the just the fact that there's many baryons stay there. But yeah, I agree that that our simulation is not adequate enough because we have them we don't consider the baryons to be dynamical. And
I mean, it's of course it's like a first order, to see interesting thing could happen. Sure, yeah. Okay, so you said that paper. Okay, actually consider everything a more realistic setup.
That's right.
Perhaps just have one last question, if in case nobody else has, and then we can thank the speaker again. When you were doing the estimates to see if you were getting the black hole, I think in considering the gravitational instability and particularly in general relativity, you arrived that the dispersion have to be very, very large, right? Like 0.57 of the speed of light. So yeah, is this gonna part one of the question, is this gonna be on your paper that is coming up, and no, this is in your previous paper.
Yeah.
And question two, does that affect, these relativistic or almost relativistic velocities? Does that affect your assumptions about Maxwell-Boltzmann? And if you considering so far elastic scattering, right? If you embed this in a model, would that open annihilations, or because you can probe the tail and have sufficient energy to do number changing interactions? Or I'm just wondering how solid it is to have Maxwell-Boltzmann with such large velocities.
Oh yeah, so good. So first let me clarify this plot is our published paper, the posted paper. You can find this plot, and which is a part of our in our full story. And so in our paper to appear, where we consider a Maxwell-Boltzmann distribution, Oh, good. So I think this condition is sufficient when the contract how to say, in some sense, we consider Max-Boltzmann distribution in a relativity sense, which means the energy we considered is not only have the kinetic energy, it's also have all the like a full momentum contribution there. So in that sense, it contribute. I think your question is more asking like why we don't consider some like a Fermi-Dirac or like
that's part of it,
Einstein distribution. Yeah,
that's part of it. But also, if you have some 2-to-2 interaction, term that could also produce I'm thinking a 2-to-4, for example, in some basic scalar. And if you have these particles have enough energy, which you might because the dispersion is so large.
Oh, you mean there are some particle pair production?
Right.
Process?
You start to take into account number changing interactions, in some chemical processes, et cetera, right? So how solid things are with these relativistic systems?
Yeah, very good. Like the honest answer is that we try to avoid all these complications in our our discussions, but those complications, of course, as you said, exist. And so I can see just for some part of parameter space, there may be a part of parameter space where the pair production is still not sufficient. Because maybe just because your dark matter is too heavy, you cannot pair produce them. And also the occupation number is large enough that you don't need to consider it's like that plus minus one from Maxwell, from Fermi-Dirac or Bose-Einstein. And we identify there's some parameter space regions there. And that parameter space region seems can be connected to the gravothermal story. So we are kind of happy with that. Of course, if we want to scan all the parameter space, we also need to consider all these quantum effects and all the pair production effects, and that will be very interesting. But we just leave it for the future.
Yeah. Okay. Good. Thank you, Yiming. Any more questions? If not, whoever's left, let's thank Yiming again. Thank you for the interesting talk, Yiming. Clap, clap. And
thank you very much.
To see you. And I'm looking forward to seeing the companion paper.
Okay, thank you.
Thank you. See.
Bye-bye.
Yeah, most people have already left, but thank you.
Yeah.
Thank you, Gigi. Thank you for your invitation.
Yeah. Oh, by the way, and on our project, I think I understand now the little phenomenon that's going on with the electron scattering. So I'm gonna start writing now section 3. I got hold up about that, but yeah. So I'll keep you posted.
Okay, great. Yeah. Okay.
And if you can get on going on some appendices or something, like just don't feel. I separated this into different sections so you can write some while I'm writing something else.
Yeah. Sounds good. Yeah.
Right.
Okay. Yeah, I will do that. Especially now I'm like more free.
Yeah. No pressure. I think I understand now this, and so I can start writing section 3. All right. Take care.
Okay. Thank you. Bye.
Thank you.